So we saw Fourier transform, its properties, and the important aspect of Fourier transform for us was that the phasor was the eigenfunction of an LTI system, and the phasors are what we used as the basis for Fourier transform, and we expressed any possible signal that satisfies Dirichlet conditions, or in some cases using Dirac delta even when it does not satisfy Dirichlet conditions. We expanded those signals in terms of phasors. So Fourier transform is basically nothing but a representation of time domain signal in terms of phasors, which are orthogonal. Okay. So with this representation, we were able to simplify the analysis of LTI systems. In particular, for us, the application was RLC circuits. So we were able to simplify the analysis. Basically, we saw that we can quantify the RLC circuits as impedances. So instead of writing complex equations with integrals and differentials, Fourier transform helped us to transform that into set of polynomials. Okay. So we can just write a particular KVL equation or a KCL equation just as a set of polynomials instead of writing that as set of differential equations. This was the main applications that we saw. It helped us to solve ordinary differential equations which appear in RLC circuit analysis. So finally what we did was we just applied this Fourier transform to RLC circuits which are in the form of impedances, and we had a rational expression as the frequency response. So if we wanted the frequency response, we can just stop there, or we use partial fractions and then find out the impulse response. Once the impulse response is known, then we can compute the output of the circuit for any possible input just by convolving with that. So this is the main usage of Fourier transform for us in electronic circuits. But the important drawback that we had was, what if the Fourier transform did not exist for a particular signal, or for a particular circuit? Let us say it had an impulse response which did not satisfy Dirichlet conditions and which could not be computed using even Dirac delta functions. In that case, how do we proceed to analyze this circuit? So in that case, Laplace transform helps us. So basically, Laplace transform is used in cases where Fourier transforms do not exist. So let us see Laplace transforms. So when do we say that a Fourier transform do not exist? So there are several conditions, but the most important factor when a particular Fourier transform may not exist, for example, if you consider the signal e power at u of t or just e power at, this obviously does not satisfy the Dirichlet conditions, and even with Dirac delta function, it becomes difficult to compute the Fourier transform. The Fourier transform does not exist. So when you try to compute the Fourier transform of this signal, the Fourier transform does not exist. Then if this is an input to our circuit for some reason, how do we analyze that circuit? It is not possible. So this is where Laplace transform comes into picture. So whenever a signal is aperiodic, if it is periodic, obviously Fourier transforms can be computed because through Fourier series. If it is aperiodic, then Fourier transform may not exist if it is containing infinite energy. So this is the most common case where the signal is aperiodic and containing infinite energy, where Fourier transform will not exist. So in that case, Laplace transform says that, well, if we can somehow convert that to a signal with finite energy, then we can just simply use the Fourier transform tools itself to do the analysis. Is there a way of doing that? So what Laplace transform says is, take any signal x of t. If it is an aperiodic signal and it has infinite energy, multiply that with an exponentially decaying signal, that is e power minus sigma t. So what are we doing? So we are just simply multiplying that with an exponentially decaying signal. Let us say our x of t is something like this, and we multiply that with an exponential d. How does e power minus sigma t look like? It looks something like this. So when you multiply this, what happens to portions on this side? It starts decaying. Right? The resultant here is the product of x of t e power minus sigma t. So it starts decaying. So because of this decay, so we are saying that it should be possible that this signal might become absolutely integrable, or it might have a finite energy. So typically most often we will look into signals which are right-sided. So for that reason, we'll just multiply with e power minus sigma t. Of course, because e power minus sigma t can keep growing on the left-hand side. So Laplace analysis makes more sense for signals which are right-sided, so that if we have a signal like this or something that starts at a finite time on the left-hand side, then it makes more sense to use Laplace transform for that. So we'll consider ourselves in this case to have a signal which is mostly right-sided. So the idea in Laplace transform is that you multiply the signal with an exponentially decaying function by creating a new signal. So let us say that some z of t is equal to this new signal. Now find the Fourier transform of z of t, because we have created this z of t such that it is absolutely integrable. So Fourier transform will exist. So that is what we are doing. So you compute the Fourier transform of x of t times e power minus sigma t, which is basically the Fourier transform equation that we have here. And we'll say that now this is not only a function of j omega, because you can change j omega, but also you can change sigma here. So you can change sigma and j omega. So the spectrum that we have now is a function of both j omega and sigma. And what is the sigma? The sigma is basically the exponent of decay of this function that we are multiplying with x of t, so that this entire signal is absolutely integrable. Now let us say that s is equal to sigma plus j omega. We are changing the variable, right? So instead of writing sigma plus j omega every time here, we'll simplify our life. So we'll call this as x of s. So this is what we refer to as the Laplace transform. The Laplace transform of x of t is given by x of s, which is basically nothing but x of t times e power minus st, where this s is a complex number. If this s was a purely imaginary number, then you get the Fourier transform. If this s is a complex number, then you get Laplace transform. In some sense, this is like a generalization of the Fourier transform, right? So in the Fourier transform, we said we'll just simply use phasors. So instead of phasors which contain a constant magnitude signal, what if you also include in the basis different signals which also contain different magnitude? So the signals e power minus st that we consider here are not orthogonal like what we consider in Fourier transform. Okay, so we cannot directly use those theories here. So we don't have Parseval's theorem and all to be present in Laplace transform, because these are not even orthogonal anymore. So we cannot consider those vector analogy here or the Parseval's theorem here. So basically what are we doing? We are just simply taking the time domain signal, decaying it with some exponent, and then computing Fourier transform. We are simplifying that as x of t times e power minus st. Okay, so the simplified expression looks like this. It does not mean that we are expanding in terms of these exponents. Okay, so keep that in mind. Okay, so now we have Laplace transform, though there should also exist an inverse Laplace transform, right? So what is inverse Laplace transform? How did we get Laplace transform in the first place? Through Fourier transform. So we can do inverse Fourier transform, right? So if we apply inverse Fourier transform here, we should be able to get back this signal. So let's do that first. So to get back the signal x of t times e power minus sigma t, you apply inverse Fourier transform, which is just this expression. You take x of sigma plus j omega and then multiply with the phasor, and then of course there is a normalization term. This is inverse Fourier transform. Now we know that this is just x of s, and this e power minus sigma t, you can bring it to the other side. So if you bring that to the other side, what do we get? So you just have e power plus sigma t. Now you can bring this inside integration because there is only a constant with respect to omega. So you can just bring that within the integration. Now once you bring that, now these two exponentials you can combine together to write as e power st. Okay. So one thing now is we can change the variable of integration from omega to s. So what is s? S is equal to sigma plus j omega. So what is d omega? D omega is 0 plus So d omega is related to ds in this fashion, which means if we have just d omega, then we have to replace this d omega with ds by j, and that j comes here. So this is the expression for inverse Laplace transform. So this is the inverse Laplace transform. Basically, this is just Fourier transform. All we did was only Fourier transform. Only thing is, instead of computing the Fourier transform of x of t, we computed the Fourier transform of x of e power minus sigma t. That's all. And you also do the same thing for inverse Fourier transform. And you do the same thing for the inverse transformation also. So if you do the same Fourier transform for the forward transformation and the reverse transformation, only for x of t e power minus sigma t instead of x of t, we get Laplace transform. So if you remember Fourier transform, you also know Laplace transform. Okay. So the simplification is that, so you can directly find Laplace transform just by integrating with e power minus st, and you can find the inverse by this expression where you are integrating now from sigma minus j infinity to plus j infinity. Earlier we were simply doing minus infinity to plus infinity because the order of integration was dependent only on this variable which was omega, which is the frequency. But now it is s, which is a complex number. It is not a real number anymore. So omega here was a real number. So we could just let it go from minus infinity to plus infinity, whereas here this s is a complex number. So how are we integrating? So we have to integrate over the complex plane. So let's call this as the S plane. Okay. So there is a sigma, which is the real part, and there is also this imaginary part omega. So earlier we were integrating along this line, basically sigma equal to 0 line alone. So there was no issue. Now we have to integrate along a different line. So that line is, let us say, some sigma naught. So basically it is some sigma naught or some line. You pick some value of sigma and you integrate along that line. So that is what we mean by inverse Fourier transform having limits sigma minus j infinity to sigma plus j infinity. So technically it is still from minus infinity to infinity, but it is not along this line, but it is along a different line, because you are doing the integration now over a complex number, not over a real number. Now there is another question, what should be the value of sigma? So we said that, okay, x of t does not have a Fourier transform. So we will construct z of t such that you multiply this x of t with an exponential which decays. But what should be the exponent of this exponential? How to choose this? For what values of this exponential will this Laplace transform also exist? So when you say Laplace transform exists, it means the Fourier transform of x of t e power minus sigma t exists. So whenever the Fourier transform of x of t e power minus sigma t exists, then the Laplace transform also exists. So basically, what are the choices of sigma for which we can say that this Fourier transform exists? So this set of choice of sigma is what we refer to as the region of convergence.